Hi everyone! Today we're going to be talking about Euler's method. And really what we're going to be doing is trying to get a better understanding of it conceptually. So here I've written out the equation for it. So let me remind you, basically what you're trying to do is solve for the next step, so the next point, yn plus 1, when you already know yn, so the previous point, and then you've chosen a step size h, and then you also know dy dt, so the slope at the previous point, yn and tn. So basically, we want to have a better understanding of the structure of this equation and why it's useful. So basically, we're gonna keep track of this graphically, because I think that'll help. So we'll have t at the bottom, y here, and we'll really try to get an understanding of what we're doing at every step. So we're starting at t0 and y0, so we're given some point, right? Okay. Okay, so we're starting at t0, and we know y0, so we're looking for y1. So at every point, what you're really doing is you're constructing a line. So if you think about it, the components of this are really the components of a line. So this yn, that's really like your intercept. So your b, right? When you have the equation of a line, it's dependent on some y value, right? So your b. And then your h, so the h is your time step means, so for some small time step, you're moving forward by that value. And that's so our x-axis is time, right? So this is delta t, right? So for moving forward in time, each of these is separated by h. Okay. So you can think of this as our x, right? So on the x-axis. And then this piece, dy dt is literally a slope. So you can think of that as your m. So you're taking the slope at your previous point, and then you're constructing a line using that slope and moving forward until your next time point. So that's dictated by your step size h. Okay, so this is simply a line. So y equals b plus x times m, or mx plus b as you're used to. Okay, so let's look at this step by step as you're constructing your solution using Euler's method. So you're starting at t0 and y0, right? What you're doing is you're calculating your slope at that point. So at the previous value, that'd be y0 t0 here. So say you get something like this. Okay, that means that you're using Euler's equation. You're going to calculate this line up until you hit t1. Okay. Then y1 is just the value you hit from that line. Okay. All right. Then, at that point, you reevaluate. So Euler's method basically assumes that for a small enough step size, if h is small enough, then your solution y is approximately linear. And that it's assuming that if h is small enough, then you're reevaluating often enough that you're hopefully staying close to that curve. So your approximation is hopefully pretty accurate. So the key part is that h is small. Okay, so now we've gone h out, t1, we got to y1. Now we get a new slope, right? So we look here, calculate dy dt now at y1, t1. So we might get something different. We might get something like this. Okay. Now we construct a new line. We use this slope. We use t1 and y1. Okay, so we're using y1 plus h. Okay. Using that slope, and we might go out to t2. Okay, so t2 now tells us where y2 is. Okay. Now we calculate dy dt at this new point, and we might get something like that. Okay. So we construct a new line. We get our next point, y3, which might not be much higher than y2. Okay, so that's the process. So at every point, calculate a new slope, construct a new line. But Euler's method, that's the crux of it. It's basically a line, and at every point, you're assuming that if you have a small enough step size, that your solution is approximately linear. So let's look at the relationship with step size. Okay. So down here, let's look at just one step. So I'm going to say, like, say we know a true solution. Let's call this y true. So we want to compare Euler's to some solution we actually do know. Okay. So say we're starting here. This is t naught. Okay, and we haven't really chosen a step size yet, so we want to look at a couple different candidate h values. Okay, but no matter which we choose, the slope here is the same, right? No matter what we choose, that's the line we're looking at. And then h will just dictate how quickly, like what point we use. Okay, so if h is really small, I don't know, say h is here. I'm going to call that h1. Okay. Then that'll be what we're looking at from Euler's method. I don't know how well you can see that point. Okay. But if we took a bigger h, say that's our h2 up to here. Okay, then that's pretty far off the curve, as you can see. So I'm going to call this is where the true value hits. So this is going to be our error 1. This would be error 2. And that just comes from how big our step size was. So as you can see, for the smaller step size, the assumption that the function is approximately linear seemed closer to true. You can see that it's pretty linear here, and then for a bigger step size, it started to curve here, but our straight line obviously didn't. And so what you guys are going to get into in class is accuracy. So you'll talk about the accuracy of Euler's method and specifically what the relationship is between step size and error. So yeah, I'll let you guys look at that in class.